I think we deal with topic 22. And this topic deals with so that is not here. With this beam that is simply supported at both ends, and there is this P sub 0 sine omega t. So that is an excitation. So we wrote down this equation, differential equation, d for w dx in force power plus rho a d2w dt square equals qy of x, distributed load, which equals minus p0 sine omega t times delta function x minus L over 2. Okay, then we wrote w of xt equals wk of x, then phi k of t, k from 1 to infinity, where this is a mode shape for free vibrations. And this is an unknown function. Okay, so that should be determined. And then we substituted this into this series. So that is a series solution. Okay, that is infinite series. So we substitute this there and we get EI, force derivative of this product. So that will be force derivative of WK, x in force power, times phi k. So this has summation k from 1 to infinity. Then plus rho a, second derivative, it's w. So that will be, so this summation, k from 1 to infinity. Second derivative with respect to time gives me d2 phi k dt squared times wk. And this equals minus p sub 0 sine omega t delta function x minus L over 2. Yes. Okay, then the rest I will do myself now. Thank you. Oh, I better take out this pencil. Can also give you some things. And some more. Oh, actually I found this pages here in between. Oh, it's good. I did find them. Okay, so then we said that now we talked about delta function of x minus a, anything, or x minus alpha. So this delta function is a function that equals 0 if x does not equal alpha, and goes to infinity when x equals alpha. But this is not very informative. Definition. Okay, is a more informative definition. So this function actually behaves like this. So this is alpha. Something like this. So it goes to a very big value. This goes to very big value when x equals alpha. So this delta function x minus alpha. You did make some suggestions that I'm going maybe sometimes very fast. So I would like to appoint some person here, a very important person who will tell me, slow down, please. So who wants to volunteer to be such a person? Maybe yourself? Okay? Say it again? Oh, for you it's okay. So can you be that person? Slow, please. Okay, fine. Thank you. So, or that could be identified like such a function, as we already talked about this function. Say, this is alpha, and around it there is this, say, p, so this distance is epsilon. And this is p over epsilon. Okay? So when epsilon goes to 0, p over epsilon goes to infinity. Okay? So function is 0 everywhere, but is infinity here. Then better definition. How it acts in concert with other functions. Other functions. So that is the main thing. So we take x, delta function x minus a. I multiply it by some other function, f of x. Integrate between 0 to infinity, dx. So to what is this? So I will explain you. So imagine I took this alpha and this, I represented it like this, p over epsilon. And I multiply here by f of x. Okay? And I want to integrate. Integrate, say, between minus infinity to plus infinity, p over epsilon f of x, now dx. Now this actually equals alpha minus epsilon over 2, alpha plus epsilon over 2, p over epsilon f of x dx. Now but this integral everywhere is 0, so only here it is not 0. So in this region, f of x varies very little. F of x varies very little. F of x varies very little. So therefore, it's like a constant, so it can be taken out of integral. So therefore, what has been taken out of integral? Taken out of integral at this value alpha. So then it equals f of alpha, and then integral alpha minus epsilon over 2, alpha plus epsilon over 2, p over epsilon dx. And this guy, of course, equals p. So the main thing, so then we define it like this. Delta function x minus a, f of x dx, from minus infinity to plus infinity equals f of a. So question, what does delta function do? Answer, it takes out from the function its value at x equals a. Function is something. So look, this is like function f of x. Delta function takes just one value from it. That is what delta function does. Dirac's delta function. So we go back to what we had here. We have this expression. Okay? We multiply this expression by W m of x. So I'm giving a slightly different presentation then. Or more specifically, we have EI summation alpha from 1 to infinity. First derivative of W, that is k pi L in fourth power, then sine k pi x over L phi k of t. That is the first one. Then plus rho a, k from 1 to infinity, d2 phi k, dt square. Wk will be sine k pi x over L. And this equals minus p0 sine omega t, delta function x minus L over 2. Omega is excitation frequency. Now we multiply each of them. See, color is very helpful here. Sine m pi x over L. Sine m pi x over L. Sine m pi x over L. And we integrate it between 0 to L. Integrate this between 0 to L dx. And this we integrate between 0 to L dx. That is what we do. So then what we already talked past time, that this function, okay, m is fixed. Fixed. Okay? So m, we know what number it is. It's 1 or 2 or 1,000 or whatever we want. Million. Then from this summation, this integration gives everywhere 0 unless k coincides with m. When k coincides with m, this integral equals L over 2. So that means that every term is 0 except only one term, which is m's term. Okay? So that is k from 1. So we have EI, then we have m pi over L in force power. Sine and sine together will be L over 2, phi k of t, plus rho a, d2 phi k, I said phi k, phi m. K must equal m, phi m, dt square, L over 2. Here on the right hand side I have minus p0 sine omega t. And now delta function will give me sine m pi L, and here is L over 2. Okay, so that is a definition. I have to substitute instead of x L over 2, and that is how what we'll get out. Now we divide everything by L over 2 and rho a. So we get EI m pi over L in force power divided by rho a, and L over 2 will be gone. Phi m plus d2 phi m dt square. This equals, divided by L over. My question to you, yeah, that is together. So here we have minus p0 sine omega t times sine m pi over 2. And we have to divide by rho a and L over 2. Okay, that is solution for phi sub m, where m is fixed. Now this thing is nothing else but m's natural frequency, that is omega sub m squared. We studied simply supported beam, and we know that this is a m's natural frequency. You better write this because we will get some very interesting results. So then we get, I'm writing it down, d2 phi m dt squared plus omega sub m squared phi m. Okay. Now this equals minus 2 p sub 0 sine omega t rho a l sine m pi over 2. Okay. So we can find naturally for this equation, we find phi m is phi complementary solution plus phi particular solution. So phi m equals phi complementary equals C1 cosine omega mt plus C2 sine omega mt. Then particular solution equals phi m particular equals some a times sine omega t. I substitute this here, I get minus a omega squared plus omega m squared a. This equals minus 2p0 rho al sine m pi over 2. So then a equals, okay, so I can multiply everything by minus, I get 2p0 rho al sine m pi over 2. And then 1 over omega squared minus omega sub m squared. So then phi sub m equals C1 cosine omega mt plus C2 sine omega sub mt plus 2p0 sine m pi over 2 over rho al sine, okay, because a times sine omega t divided by omega squared minus omega m squared. As we see, if frequency of excitation omega coincides with any natural frequency, then solution goes to infinity. Okay, because if this equals this, any natural frequency, then solution goes to infinity. Then phi m goes to infinity. Resonance. So that means that we should try that excitation frequency should be far away from any natural frequency. We should try that excitation frequency is far away from any natural frequency. Okay, but we are still not done, by the way. Now we found phi sub m, is it not? We found phi sub m. Okay. Now we need Wx of t. Wx of t equals what? Wk times phi k of t. K from 1 to infinity. So I found phi sub m, but m is fixed. So therefore, for phi k, I can substitute that expression that I found, because phi k is just any k. So then I get, so this equals sine k pi x over L, k from 1 to infinity. And then I substitute the whole expression for phi k. And that is C1 cosine omega kt. Look, please, I just, instead of m, substitute k. M was fixed. So I found m for m1, m2, m3, etc., for any m. So now I'm substituting this for general k. Plus C2 sine omega kt plus 2p0 rho al sine k pi over 2 times sine omega t divided by omega squared minus omega k squared. Okay, that is my expression, which is still not final. Now, pay attention here. Let us consider this sine k pi. Did we write this? Mr. Fanfan, you don't tell me to slow down. Can you get faster with telling me slower? Okay. Any questions? No. Any questions? So then we have, let us deal with what is sine k pi over 2. Okay, when k equals 2, then it will be 2 pi divided by 2, then it is 0. If k equals 4, that is 4 pi divided by 2, it's 0. So it is 0 for k even. For k even, it is 0. Yeah, now if k equals 1, then it is sine of pi over 2. How much is sine of pi over 2? 1. What happens when k equals 3? 3 pi over 2, it's minus 1. So anyways, it is 1 or minus 1, 1 or minus 1 for k odd. So therefore, final expression will be 6, 7. 7 will be wxt equals k does not equal 1 to infinity, 1, 3, 5, 7, etc. to infinity. Then sine k pi x over L. And C1 cosine omega kt plus C2 sine omega kt plus etc. Plus another term. So only pay attention, because loading is symmetric with respect to the mid cross section. Mid cross section, because loading is symmetric with respect to the mid cross section, only symmetric modes are excited. Only the symmetric modes are excited. Symmetric modes means 1, 3, 5, etc. Remember, that is the first mode. That is a third mode, etc. Then this is a fifth mode. Etc. So we see that natural frequency is part of the game. Natural frequencies appear in analysis. That is why we studied and will study a lot natural frequencies for forced excitation. Again, why do I need natural frequencies? My ultimate goal is not natural frequencies, but my ultimate goal is response. In order to find the response, we need natural frequencies. Okay, do we have the homework number? What is our homework number set? 12, okay. So I would like us to solve the following problem. So this Q of xt equals Q sub 0 sine omega t. Okay, find Wxt by series method. It is also called normal mode method. Second, I would like to ask you the following problem. So that is middle. L over 2, L over 2. So this is L over 4. Load is applied here. Load is applied here. P0. And here is also P0 at a distance L over 4. Okay. I will just write it down for this differential equation. Will be EI d for W dx in force power plus rho A d2W dt square. This equals P sub 0 times delta function x minus L in force power minus P sub 0 delta function x minus 3/4 of L. Okay? Draw conclusions in both cases. Yes, just 1 second. Yes? Too fast? Say it again? Yeah, load should be, this is 2 concentrated loads. But 2 concentrated loads, I would like to write it down as distributed load. Means which modes are excited. Okay. Yes. Yes. In order to underline this, I will write it down here. Yes. Any questions here? Oh, I see. Yeah. The question is whether this load is uniformly distributed. I see. Okay. So, student is asking whether this load is constant or variable. This load is constant for any value of t. I'm showing the beam in space. So for every value of t, this is a constant load. It is q0 times sine omega t. So whatever value of sine omega t will take, that value should be multiplied by q sub 0. So actually it is variable in this direction. So it's or this, or maybe more, maybe less, positive, negative. But every time, for any time instant, it is a constant. It is. So we did not show here time also. What happens with time? We showed only in space. Any other questions? Yes, sir. Okay, my student is asking whether or not right-hand side is written as a distributed load. Yes, the answer is yes. This is written as a distributed load as we did before. Before we had just only one load and we had it in the middle, so we had it at L over 2. So now we have two loads, so we have to sum up. Now one load is in one direction, the other in opposite direction, so different signs. So we have P0 delta function. So there is a big concentration as if of force here and here. Okay? We represent distributed load. We represent something that is concentrated. This is like string with two masses. Here is like positive mass, negative mass, something like that. So therefore I represented P sub 0 delta function x minus L over 2, and then a P sub 0 delta function x minus 3/4 of L. Is there any problem? No. Any other questions? No. Okay. There are some other methods of determination of this problem, okay, of analogous problem. And I will deal with this now. So this will stay with me, and we are continuing. So that is 7. 8. Do we have page? Yes, 8. At 23, is it not? Topic 23. Using property of symmetry. And this is like this. I have this beam, and here acts this load, P sub 0. Yes. P sub 0 sine omega t. Now, pay attention that here there is no load. So that means that it's free of loading. And here it's the same. So now, if I depict the shearing force, Vy of x, so at this location, there should be some jump down. Now, this jump, of course, equals P sub 0, P sub 0 sine omega t. But because the system is symmetric, Vy should equal here half of P sub 0. Okay, so something like that. So this is P sub 0 divided by 2 sine omega t. And this guy is minus P sub 0 over 2 sine omega t. There is no other way, because jump should equal the force. Now, this is a symmetric system. In the symmetric system, that is how it should be. So this, when I come from here, I should see positive value of something, and when I go from here, I should see the same value but negative, because system from here or from there looks the same. Therefore, we can deal with this system as free vibrations, but with boundary condition at x equals L over 2. So what will be the condition? Look, please, at x equals 0, w, of course, equals 0. And second derivative of w with respect to w of x is 0. Now here, behavior must be symmetric, because I see that there is a symmetry. So therefore, that is a displacement. Because displacement is like this, here derivative must equal 0 underneath the load. Maybe I will find, I have somewhere. Okay. So this derivative must equal 0. So therefore, conditions there are at x. So at x equals L over 2, dw dx must equal 0. And the load, EI, third derivative, so that is w with respect to x cubed. So that is a shearing force, must equal just P sub 0 over 2 sine omega t. So I have a inhomogeneous boundary conditions. I have here something. This red is here. I was looking for it. Okay, so therefore, I actually deal with the following problem. Look, please. EI d4w dx in force power plus rho a d2w dt square equals 0. Then boundary conditions w at 0 equals second derivative of w at 0 equals 0. W at, okay, then dw dx at x equals L over 2 equals 0. And then I have EI d3w dx cubed at x equals L over 2 equals minus p sub 0 over 2 sine omega t. So this is my problem. Now we substitute w, instead of w, we substitute capital W of x sine omega t. Then we get the different problem. EI d4 capital W dx in force power minus rho a omega square w equals 0. Then capital W at 0, capital W second derivative equals 0. And d capital W dx at x equals L over 0 equals 0. And one more, EI d3 capital W dx cubed x equals L over 2 equals minus p0 over 2. There is no signs are gone. Sine omega t is gone because I introduce sine omega t everywhere, so sine omega t is gone.